So what if you have a sample and it's just a clear liquid and you have no idea if it's a carboxylic acid? How do you connect the things you can hold in your hands and see with your eyes with the concepts and the structures that we've been drawing all through this chapter? And the bridge that spans that gap is spectroscopy. Now, here we're going to have three types of spectroscopy. We're going to have mass spectroscopy. We're going to have IR spectroscopy. And we're going to have Nmr spectroscopy, both hydrogen and carbon, 13 Nmr spectroscopy. And each of those tell us different things. The mass spectrum tells us the molecular formula, or at least lets us come up with a plausible molecular formula. We can validate that molecular formula by using the other two types of spectroscopy. The IR spectrum tells us about the functional groups, so ketones, aldehydes, carboxylic acids, alcohols, amines. And the Nmr spectroscopy tells us how atoms fit together based on the electronic environment that they are in. So for the mass spectrum for this exercise, how all of these work, of course, we spent whole chapters on. But for this exercise, for the mass spectrum, you want to know two things. You want to know how the M+1 peak relates to the molecular ion peak. And you want to know what the M to Z value ratio means. The M+1 peak tells you how many carbon 13s, how many places in your molecule you could have a carbon 13. 98.9% of all of the carbon on 98.9% of all of the carbon on Earth is carbon 12. 12 protons, or 6 protons, 6 neutrons. 1.1% is carbon 13. In order to be carbon, it still has to have 6 protons. It just has 7 neutrons now, so it's a little heavier. Well, that makes the mass of the overall molecule heavier by 1 atomic mass unit. And so any place where you have a carbon in a molecule, you have a place where you could be contributing, 1.1% of the time, contributing an extra mass unit. Well, that extra mass unit is the +1 here. So 12 plus 1 is 13. So the mass of the overall molecule plus 1 carbon 13 will give you the M+1 peak. And because for every carbon, there's a 1.1% chance that you'll have carbon 13, the relative peak of the M+1 peak to the molecular ion peak tells you how many carbons you have, how many places where you could possibly have a carbon 13. If you only had 1, then it would be 1.1%. If you had 2, it would be 2.2%. If you had 3, it's 3.3%. So what we know here is that we have 3.3%, or we have 3 carbons. So if we sort of think of we know we have carbon, we'll have 3 of them. And each weighs 12, so that's 36 mass units coming from carbon. In other words, whatever the percentage is of the M+1 peak to the molecular ion peak, divide it by 1.1, and that gives you the number of carbons that you get. Okay, so that's the first thing you need to be able to get from a mass spectrum. The number of carbons. The second thing you want to get is what the MZ value is for the molecular ion peak. M to Z, that means mass to charge ratio. But the charge ratio is usually +1. If it's bigger than that, the molecule crumbles in the spectrometer, usually before it hits the detector. So it's usually the M to Z ratio is usually +1. Not all the time. If you go on in further in chemistry, you'll see cases where it's not. But most of the time it's +1. For our class, it will always be +1. So the M to Z ratio really gives you just the mass. And so the overall mass of our molecule is going to equal 74 AMU. So this is the information that we get from the mass spectrum. Now we have to do a little bit of interpreting in order to come up with a plausible, to use this to come up with a plausible molecular formula. So first, we need 74 mass units. The most abundant element in the universe is hydrogen. And you can tell by how much water there is on the surface of Earth. There's a lot of hydrogen on the surface of Earth. So can we fill in this gap from 36 to 74 just with hydrogen? Well, we know hydrogen weighs 1. We know that we would need an extra 38 mass units. Can we put 38 hydrogens on 3 carbons? No, we cannot. And so we have to add another element. Now, the next most prevalent element on Earth is oxygen. So that's, and again, we're just coming up with a plausible molecular formula, so that seems like it would be a good guess to put on the molecule. Well, oxygen weighs 16 mass units. What if we just put 1? Then we'll have 16, and together, 36 plus 16 is 52. So we have 52, we need 74. That means that we would have to have 22 units coming from the hydrogen. Can we fit 22 hydrogens on 3 carbons and 1 oxygen? No. So we have to go back to the drawing board. What else can we add? We can add a second oxygen. So 2 oxygens, that gives us 32 mass units. So now this overall mass is 68, and we'd only need 6 more mass units to get 74. So we'd only need 6 hydrogens, and we can definitely fit 6 hydrogens on 3 carbons and 2 oxygens. So a plausible molecular formula will have carbon, hydrogen, and oxygen in it. And the number of carbons will be 3, hydrogens 6, and oxygens 2. 3, 6, 2. Okay, so that gives us a plausible molecular formula. That's the most information we could get from the mass spectrum. Okay, next. How about the IR spectrum? The IR spectrum tells us about functional groups. And you would, of course, still want to keep in your mind, as a good chemist, all of the peaks, all of the signals that we saw before. A sharp peak at 1700 is a carbonyl. A weak peak just to the right of 3000 is an alkene, etc. For this chapter, the carboxylic acids are what we're going to be dealing with. We're dealing with the carboxylic acid. So to know whether you have a carboxylic acid or not, you would look at the IR spectrum. The carboxylic acid has 2 bonds. The carbonyl, carbon to oxygen double bond, will absorb light at around 1700 wave numbers. Now, that is different for different functional groups. So if you look in the homework, I put a nice table there, and you can see how they're all kind of around 1700, but depending on the exact functional group, they will absorb at slightly different places. For our purposes, though, we're going to focus on carboxylic acids. These tend to be closer to 1760, but you can remember from previous chapters, as a sort of context provider, that the carbonyl oxygen aldehydes and ketones is usually around 1700, and it's similar here. So 1700 generally is what you would have known. We have carboxylic acids here. That'll move that up to around 1760. The other bond that we have is the bond between the carbon and the oxygen on the carboxylic acid. That bond is really, really broad. I mean, we knew that it was broad before for alcohols. It's around a smooth peak between 3200 and 3600. But for carboxylic acids, and what's spreading it out are the hydrogen bonds that weaken the bonding here, and give it a sort of different energy that it vibrates at, and so it'll absorb light energy at different places. So it's the hydrogen bonding that spreads it out, and carboxylic acids are notorious or are famous for forming very strong, frequent hydrogen bonds. So you could imagine sort of 2 carboxylic acids arranged. The hydrogens here are slightly positive, the oxygens are slightly negative, and you could see how they would attract each other. And you'd have lots of these hydrogen bonds. And that spreads the signal out for the OH a lot. It spreads it out a lot. It goes from around 2200 to 3600 wave numbers. It takes up around a third of the graph. so really broad. So those two peaks there, those two absorptions in an IR spectrum will tell you that you have a carboxylic acid. If you have those, you have a carboxylic acid. If you don't, then you don't have a carboxylic acid. So on this test, you don't have to worry about the other derivatives. You either will have a carboxylic acid or won't, and you'll use the IR spectrum to figure out which one you have. So here, and let me erase the mass spectrum so it doesn't confuse us and distract us. Here, they give us a sharp peak at 1700, so far, and specifically 1760. So carboxylic acid is looking good, but keep in mind, at this point, we still could have just an aldehyde or a ketone. We have to look for the broad peak between 2200 and 3600 wave numbers. Because we have both of those, we know that we have to have a carboxylic acid. Whatever else is in the molecule, we have to have a carbon double bonded to oxygen, single bonded to an OH. You can confirm this in a couple ways. You could, for example, we know we have the two oxygens, so that it's helping to confirm our molecular formula. But another thing we have here is a double bond. So if you find the degrees of unsaturation, remember the degrees of unsaturation is 1/2, 2 times the number of carbons plus 2, plus the number of halogens, plus the number of hydrogens, minus the number of nitrogens, minus the number of nitrogens. Oops. Sorry. So it's this plus the number of nitrogens, minus the number of halogens, minus the number of hydrogens. If you plug that in, you'll get 1/2 of 6 plus 2 plus 0 minus 0 minus 6. So that's 1/2 of 2 is 1. And we just have one double bond there. So we get that we also get that sort of information from the molecular formula that we got from the mass spectrum. So now we're here. We have a pretty good idea that we have a carboxylic acid, and we just have 2 more carbons to go there. Now technically, in this particular problem, there's only one other way you could fit 2 other carbons on here. One of them has to attach to this, and the other one only has one other carbon it could attach to. So you could just stop here and say, well, I have propanoic acid. But let's assume you didn't have that connection, or let's assume you had a molecule that was bigger than that, which you very well could on a test. How could you figure out what the branch would look like? There are 3 patterns you really want to remember for proton NMR spectroscopy, splitting patterns. If you have a triplet and a quartet, that is a strong sign that you have an ethyl group, especially if the triplet has an integration of 3 hydrogens and the quartet has an integration of 2. You can see that here. What if we wanted to know the splitting of those 2 hydrogens here? Well, they're next door to 3 hydrogens. Remember the n+1 rule. They'll split into 3 plus 1 or 4 peaks. And so you get a quartet with an integration of 2 hydrogens. How about these 3 hydrogens here? How would they split? Well, they're next door to 2 hydrogens. So they would split into 2 plus 1 or 3 peaks. And then that peak would have an integration of the 3 hydrogens in the purple. So if you ever have an ethyl group, and notice that's what is here, CH3CH2, you'll recognize that by having a triplet and a quartet with an integration of 3 and 2 hydrogens, respectively. The other 2 patterns that are really common that you'd want to know, that would be completely fair game on any test, my test or an MCAT, or PCAT, or a DAT, is if you have a doublet and a septet, especially if you have an integration of 1 hydrogen and 6 hydrogens. Oops, other way around. 1 hydrogen and 6 hydrogens. That is an isopropyl group. Right, in an isopropyl group, which looks like this, you have 1 hydrogen in the sort of middle, and you have 6 hydrogens on the methyl groups next to it. The 6 hydrogens in yellow are just surrounded by the 1 purple one, so they split into a doublet, and the 1 hydrogen in purple is surrounded by 6 hydrogens in yellow, so it splits into a septet. So, if you see that pattern, that's a sign you have an isopropyl group, and the other one you'd want to be familiar with is just one singlet with an integration of 9 hydrogens. That is a tert-butyl group. So that's 3 methyl groups branching off of 1 carbon as a branch. Because there are no hydrogens on this middle one, and there are 9 hydrogens on these end methyl groups. So you have 9 hydrogens all in the same electronic environment, and they'd have no hydrogen next to them, so they don't split at all. They're a singlet, and they have an integration of 9. So that's a tert-butyl group. So those 3 patterns you should be very familiar with. You should know by heart. Those are completely fair game on a test. So here you would see the H1nmr spectrum. You would see that and here I'll erase the IR spectroscopy so it doesn't distract us. You would see that it gives you a singlet at 12 parts per million. That's a little strange, except you would remember that the hydrogen in a carboxylic acid, it has a shift of 12. And it should make sense that that would be a singlet. There's no hydrogen next door. It has a shift of 12 because it's surrounded by 2 very electronegative elements, taking the electrons away, so it's not shielded from the external magnetic field. And also, the magnetic anisotropy from that pi bond is adding a magnetic field in the same direction as the external magnetic field. So it's really hard to flip that hydrogen nucleus. You have to shine very energetic radio waves on it. And so that's what that large number 12 is telling you. So that's further confirmation of our carboxylic acid. Altogether, the mass spectrum, which gave us a molecular formula that had a degree of unsaturation of 1, supports having a carboxylic acid. The IR spectrum, which had the 2 features of a carboxylic acid, supports a carboxylic acid. And now the Nmr spectrum with a delta of 12 parts per million, a singlet at 12 parts per million with an integration of just 1 hydrogen, is really supporting that carboxylic acid. So we are almost positive we have the carboxylic acid. Then you see the quartet and the triplet, and instantly you should be thinking ethyl group. You look at the integrations 2 and 3, so ethyl group. And lastly, the last piece of information you can get there are the shifts. Remember that a CH2 normally shows up at 1.2 parts per million. Here it is alpha to a carbonyl. It's on the carbonyl side of that carboxylic acid. So you'd add 1 and you'd get 2.2. The other CH3 normally appears at 0.9. It's beta to a carbonyl. So you'd add 0.2 and you'd end up with 1.1. So the shifts are also supporting this structure. And if any of what I just said doesn't make sense, I strongly encourage you to go back and see the videos that talk about those shifts specifically in the playlist for Nmr spectroscopy. Finally, the carbon 13 Nmr spectrum sort of just is a cherry on top at this point. It tells us how many carbons we have in different environments. We have 3, and that should make sense. We have 1 that is in a carboxylic acid. We have 1 that is immediately next to it, alpha to it, and we have a 3rd that is beta to it. Well, that's 3 different electronic environments. So we end up getting 3 peaks. And there it is, propanoic acid. We have a liquid, clear liquid, looks like water, but by throwing it into a few machines and knowing how to read the hieroglyphics that they spit out, we're able to connect that, that's propanoic acid. We're able to figure out, to connect that macroscopic experience of a molecule with this conceptual drawing of one that we've been working with, and now we can connect it with all the different recipes that we learned. We could use a thionyl chloride to turn this into an acid chloride, and then we can treat it with any nucleophile, carbon, nitrogen, hydrogen, oxygen, to turn it into a carboxylic acid derivative. Then we could reduce it, or we could oxidize it. We could add a ring to it. We could do a whole myriad of things, but it all starts with recognizing what we have in the first place, and we learn that with spectroscopy. So now that we explained one of those in detail, I'm going to go through the second one a little faster. So what we have here is an M+1 peak that's 4.4% as high as the molecular ion peak. That means we have 4 carbons. Each carbon weighs 12, and so we're going to have 48 atomic mass units coming from that. The overall M to Z value for the molecular ion peak is 88, so everything has to add up to 88. There's no way we could get 40 hydrogens, which is what we'd need, on 4 carbons. So we must have another element. If we just add 1 oxygen, it only gets us 16. It doesn't get us high enough. So we'd have to add 2 oxygens to give us 32. When we think about those two together, that gives us 80. Right, if you only used 1 oxygen, you'd have to add too many hydrogens. They wouldn't fit on the number of carbons you have. So here we have 80, and with 80 we just need 8 more. That means we just need 8 hydrogens. So a plausible molecular formula is C4H8O2. So that's a plausible molecular formula. And if you do if you draw the index of hydrogen deficiency for that, 1/2 times 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of halogens minus the number of hydrogens, if you plug that in, you end up with 1/2 10 minus 8. So that's 1/2 of 2, which is just 1. So already we're seeing 2 oxygens and 1 degree of unsaturation, so we're probably thinking carboxylic acid. But so far we've squeezed all the information we can out of the mass spectrum, and that is the molecular formula. Okay, next, the IR spectrum. Here we look for the functional group. We have a sharp peak at 1760. That is the carbonyl carbon. So far, it could be an aldehyde ketone or any carboxylic acid derivative, technically, or a carboxylic acid. Now, technically, you would want to look at these different peaks to tell the difference between these, but you'll notice that anhydrides also have a 1760 peak. So, in our class, though, we're going to be dealing just with either having carboxylic acids or not. So you'd look for the second thing, and here we do have a broad peak between 2200 and 3600. That means that we do have the OH on there. If we didn't have that, then this would be an aldehyde ketone. So watch out for that. So we know we have the carboxylic acid. So we know we have a carbon double bonded to oxygen, single bonded to an OH. Well, now we've taken care of our oxygens. We've taken care of one of our carbons. We just have 3 more. So we look at the H-proton NMR spectrum. The proton NMR spectrum, H1nmr Spectrum, has a singlet at 12, so that's confirming our carboxylic acid hydrogen, and then we have a septet and a doublet. That's the sign for an isopropyl group. So we'd have a carbon with 2 carbons. This is the isopropyl group that we discussed in the previous exercise. This one here, where you have a septet and a doublet. And we can confirm that by the shifts. So, well, first we can look at the integrations. The septet has just 1 hydrogen in it, so that's the purple hydrogen here, surrounded by 6 hydrogens, so it splits into 6 plus 1, or 7 peaks. And then we have the doublet with 6 hydrogens. There are 6 hydrogens here. They're next to just 1 hydrogen, so they split into 1 plus 1, or 2, so a doublet peaks. We can further use, and you see the integrations match those, so 1 and 6. We can further use the shifts if we wanted to be even more confident in our conclusion. The septet is representing this hydrogen here. Now that's a CH, and that normally would appear at 1.7 parts per million. But it's alpha to a carbonyl, so you add 1 and you get 2.7, and you see that's where that is appearing. If you look at the shifts for the other ones, these are CH3s, they normally appear at 0.9. It's beta to a carbonyl, so you'd add 0.2, and that gives you 1.1. And you see that that's where that appears. So everything is supporting this structure that we've built so far. Last, we can confirm this structure one last time with the carbon-13 NMR spectrum. That tells us how many carbons we have in different electronic environments. They're telling us we have 3, and we do. We have one in the carboxylic acid. We have a second one right next to the carboxylic acid, and if you notice, these 2 methyl groups are in the same electronic environment. There is symmetry here. They're both 1 atom away from this methyl group. They're both 2 atoms away from the carboxylic acid. So they're in the same electronic environment, so that's only 1 peak. So you get 3 peaks there, and that confirms our structure. So overall, the molecule we'd have is 2-methyl propanoic acid. 2-methyl propanoic acid, and now that we have that, we can use our whole arsenal, our whole recipe book of possibilities to turn that into any molecule we want.